Hello, everybody. Welcome to your free GMAT prep hour. It is August 25th, 2021. I will be your host tonight, Reed Arnold. It is my father's birthday. Wish him happy birthday. I've done one of these on my parents' engagement this year, and now I'm doing one on my father's birthday, so hooray for them. If you are looking for other free prep materials, we have them. You can take the first course of any of our courses for free, online or in person, when we start them back up in New York City shortly. You can take the first class, no charge, figure out if you like it, like the vibe, like the teacher, whatever it is. As I always say, it's 11% of our course for no money. We talk about big stuff. We clear up data efficiency and give some important strategies there. We talk about sentence correction and give some major strategies there. And most importantly, we talk about what the test is, how it's structured, how it's graded, how to study. Just a really solid stuff in class one. So even if you don't plan on taking the course, you might just want to sign up for a free class because why not? It's free. You can do a similar trial with our Interact. That's our video course, our Interact program. Really nifty, self-paced study. The videos are not like the videos you often watch where you just watch and don't do anything. You need to answer questions in them, and depending on your answer, the program will either send you to a harder question or an easier question. If you get it right, it'll challenge you. If you get it wrong, it will say, okay, well, let's dig into the foundations here. Let's spend a little more time on this problem. So really neat program, a lot more interactive than most video courses would be, hence the name Interact. So you can try a sample of that for free. Also, I'm pleased to announce that our Foundations of GMAT Math workshop is now free as well. That is a either one day for 7 hours or 2 days split at 3.5 hours, usually over a weekend, where we dig into the core foundational concepts that the test tests and talk about them in a very GMAT way. In many ways, we go back to first principles. You know, we start with arithmetic, addition, multiplication, division, and subtraction. Talk about how to think about those in a GMAT way rather than in maybe the classroom way we recognize. We then go on to other topics, but if we get to that, we really dig into the first level stuff. And so I got something out of it, and I got a good score on this test. So I think anyone can get something out of it. I highly recommend people check it out. If you can't actually make the date of the sessions, you can actually sign up and get a video version for free as well. That includes a video version of the course. It includes all of our syllabus and the books, everything you need to brush up on those foundations of math, thinking about math in a GMAT style. So that's the introduction. Now, moving on to today's topics. Today's topic. We are talking today about the GMAT's favorite equation. This is a lesson for those of you that have come to some of these. I've mentioned this a few times, and I've always mentioned that I hope to have a full session on it. So that's what I'm doing today. We're finally digging into the GMAT's favorite equation. We're going to talk about what it is. We're going to see different versions of it, see how it's applicable, and hopefully you'll leave today. In some ways, this is going to be something. It's going to be information that's not new to you. You're going to know some of this, but I hope you leave today thinking about it deeper, thinking about it in a different way, and possibly recognizing to use it in places that maybe you didn't recognize to use it before. To start off, though, I'm just going to give a warm-up question here. I'm going to give you all 2 minutes. That is the average time you have for a GMAT quant problem to do the question in front of you here. So take 2 minutes. I'm going to jump off camera, and I will come back shortly. All right, gang, that is 2 minutes. If you have an answer, go ahead and type it in the chat. If you're watching this as a recording and you want to work a little bit longer, maybe hit pause and do so. But just so you know, you should really get used to choosing a letter. And if it's wrong, it's wrong. It's okay. This isn't going to determine if you get into business school today. But you do want to get used to choosing a letter in pace because the test is going to make you do that. It's 2.5 minutes. So the answer so far, I have 3 B's and a D. 4th B, but a question mark B, so guess. 33 people in the room, 6 answers. That's E. Throw some letters up. Let's see where these answers fall, gang. Don't be afraid of being wrong. No one cares. No one will know. D, B, A, E. Okay, it's 3 minutes. Final guesses. So it's looking here like B has a slight, it's about half B, and then we have a handful of D's, handful of E's, 2 A's. No one chose C. We figured that 50-50 was a little bit too convenient, and that is probably true. 50-50 just doesn't seem like that's going to be the outcome in this case. We're going to come back to this question, though. I'm not going to actually go over this question and talk about the answer. We're going to dig into the GMAT's favorite equation, and then we're going to talk about it, see some examples of it, work on this, see how to use it, and then bring it back to that question at the end and see if we can't use what we've learned to get that question, maybe get a little more cohesion in the group. That problem had several opportunities to use the GMAT's favorite equation, in fact. And so we're going to lay out what that equation is. You might think it's going to be some big fancy reveal. It's not. It's a pretty standard equation here. Total A equals A's per B times total B. That's it. That is the GMAT's favorite equation. Okay. It is used in many different ways in many different problems. Shows up in quant, and we're actually going to see even in verbal sometimes. This is an important piece of understanding. This equation is an important rule that the GMAT wants you to know, that the total A equals A's per B times total B. And in many ways, you've seen this before. You've seen this equation. You probably already know versions of it. For instance, you might know that distance equals rate times time. Well, if I'm using miles per hour in miles, that's total miles equals miles per hour times total hours. Okay. If I ask you what distance and revenue had in common, you might not say anything, but the truth is, or you might say nothing, but they actually do have something in common. To calculate revenue, you do a very similar thing. Revenue equals price times quantity. Because what is price? Price is the dollars per unit sold. So if I'm calculating revenue, total revenue is price per unit times the number of units sold. If I'm on the flip side, total cost is the cost per unit times the total units bought. The average formula, if you remember your average formula, average equals sum over number. Well, with just a little bit of rearranging, you can turn that into this equation here. The sum of some object equals the average, however many objects per unit, times the number of items. However many items there are, objects per item times number of items. Okay, that's just the average formula. If I want to know about work, how much work is done, it's rate times time. How many jobs are completed, how many jobs completed every hour times how many hours, or if it's jobs per minute, how many minutes, whatever it is. I can do this. In many ways, you can even think of this like, or in many ways, you can think of the area formula as a version of this. Area equals base times height is a version of this equation. Okay, the area, total area equals base. If you want to think of the base as the height per unit, and the height times, I guess let's say, I want to say base. Yeah, height per unit times number of units. Actually, I think I want to flip that. I want to say height per unit of, what would that be? I've talked myself into a corner here. How would I phrase this? Height would be how high. So it would be base length per unit of height times unit of height times how many height there is. And these are indeed various different versions of an area equation. That was not a very sophisticated explanation. I apologize. That's why you don't improv. But if I think of rate times time, then the rectangle is distance, right? Rate is how many miles per hour. I probably should have done this should have put time on the x-axis. I think that would have been clearer. Let's say rate times time. If we think of rate as, how many miles per unit of time, if that's 1 unit of time, then the question is, okay, how many units of time do we have? Because that will fill up that rectangle. Same thing with revenues and costs, same thing with sum and averages. In many ways, these are all just different versions of an area equation. Another way to visualize this, however many A's there are, you think of how many A's per B times how many B's. How many miles in that hour, then how many hours are there? That's going to build a number of sets. I chose relatively simple numbers here, 15 equals 5 times 3, but I think that gets the point across. You might also sometimes see, a rate that's not nice, right? What if it's not 5 per 1? What if it's 2.5? What if the rate is 2.5 miles an hour? Well, 2.5 miles an hour is 5 miles every 2 hours. 2.5 in 1 is 5 in 2. So I could write it as either way. And if I have 3 hours, well, 3 times 2.5 is 7.5. Okay. Now, those are the standard equations, but you can use this idea in situations that we don't have formulas for. Okay, we don't have formulas for every incidence that uses a total A equals A's per B times total B. Right? You also can rearrange this formula and put all of the A's over all of the B's. If I just take that formula and divide by total B, that's going to be total A over total B equals A's per B. What is A's per B? That's a ratio. That A's per B value, that is the ratio of A to B. That's all it is. We've talked about ratios before. We have some free GMAT prep hours on ratios. If you watch all about percents part 1, that really hammers home how percents and ratios are related. We'll talk about that a little later here as well. But this favorite equation really all hinges on the idea that there's different ways to use a ratio. So I can say total A equals the ratio of A to B times total B, if I just rearrange that equation. So what I'm going to do now, I'm going to pull up several sentences or problems here. I'm going to give you all, let's say, 4 minutes or so. And what I want you to do is find how you could set up a total A equals A's per B equation for each of these sentences or sets of sentences. Warning, some of them have more than one. Some of these, even if there's only one sentence, you might be able to find more than one equation to use. Okay, so I'm going to give you all here 3-4 minutes. Just brainstorm as many as you can find. All right, gang, that's about 4 minutes. If you're at home and you want to keep working, hit pause. Suspect you haven't found all the ones you can. Okay. So keep brainstorming, see how many of these, how many versions of this equation you can find. So let's start with the first one here. A store sells one item at a fixed price. What versions of the favorite equation can we use for this first sentence here? Type in the chat. The more you type, the more we'll get through. Total price, quantity times price. There we go, Blanca. Total equals 15 times 5. I think that might be maybe the wrong one. Profit equals quantity times price. Yeah, good correction, Robert. Not profit equals quantity times price. Revenue equals price times quantity. Okay. Then I can use revenue to calculate profit if I want to. But for revenue, I would say revenue equals price times quantity. You could, I mean, I guess now that you mentioned revenue, I could think about the total cost. The cost to the store would also equal the cost per item times quantity. You could use a similar equation to get the cost of each item and then use that to get profit. Okay. Where P is the per unit price and C is the per unit cost. Okay. Good. Notice there's no numbers there, right? There's no, I don't actually give you any values and I don't assign any variables. I don't, I'm not asking for a question, but the recognition of a store selling things at a price, that just immediately brings up revenue equals price times quantity. How about there are 15 times as many students as teachers? How does the GMAT's favorite equation fit into that sentence? Total sum of what, Sean? Yeah, total students equals 15 times the number of teachers, where S is total students and total teachers. Good. She traveled at an average rate of 50 miles an hour. That one should be more familiar to y'all. That is one that's a formula you've memorized. What equation could we build out of that? Yep, total distance equals rate times time. So that would be here, distance equals, we actually have the rate, so 50 times time. Okay. The house was priced at $100 a square foot. What version of the equation can we use here? Total price, so say price equals the price per square foot, which is 100 times the number of square feet, which let's call S. Total price, 100 times total square feet. Very good. Sarah's wage is 12% more than Jessica's. Sarah's equals 1.12 times Jessica's. Now we'll talk in a second about why that actually is a version of the GMAT's favorite equation. Now everyone will be like, I think that's different, but it's really not. It's actually the same game, just a little bit different presentation. Okay. machine A takes 4 hours to complete a task, and machine B takes 3 hours to complete the same task. Okay, we have a work equals rate times time situation. So total work, which is a task, right? The job. Let's call it one job. Equals the rate of A times 4. And for machine B, the job is the rate of B times 3. Now, Danielle has also noticed something else here that's interesting. There's actually a third equation I can build. A third GMAT's favorite equation using these two equations. When things work together, as many questions formulated like this turn into, the machines that work alone end up working together. It's very inspiring, the community of the machines. When they work together, we can think about how long it takes them to do the job working together. And here, if I divide by 4, I can see that 1/4 is A's rate and 1/3 is B's rate. Right? That means, B does 1/3 of the job in an hour, since my units are hours here. A does 1/4 of the job in an hour. Well, if they work together, then in 1 hour, I can add their time. I can add their rates. If A completes 1/4 of the job, and I'm sorry, if A completes 1/4, yes, A completes 1/4 of the job, and B completes 1/3 of the job, together, 1/4 plus 1/3, that's 3/12 plus 4/12 is 7/12. And so then I can actually solve for the time. The time is 12/7. 1 hour and 5/7 of an hour. Okay, so we can use the idea of adding rates together to form a new version of the favorite equation. There are 10 ounces in a bottle. Well, you'd probably say total ounces would be 10 times however many bottles there are. 10 times B. Okay. We'll talk about that next one here in a moment. That's a more complicated problem. But real quick, I want to go through some of these and show how the favorite equation, the GMAT's favorite equation, might show up in other elements of a question, other places you might use it. For instance, let's go to the one with Sarah's wage. What exactly is a wage? Definitionally. It's a rate per hour usually. Dollars per hour. So if I'm talking about Sarah's wage, and wage is dollars per hour, what favorite equation, what version of the favorite equation could I use, could I find? So I see revenue equals price times quantity. I think I know what you mean, but yeah, good, Daniela. I can talk about Sarah's total income. Sarah's total income. Let's call income S is going to be whatever Sarah's wage is, which it's 1.2 Jessica's wage. Since we've chosen J, let's do that. That's Sarah's wage times however many hours Sarah works. Similarly, I can say Jessica's income equals Jessica's wage times Jessica's hours. If I were doing writing, which would probably be a little more realistic here, I'd say, income Sarah equals 1.12 times Sarah and income Jessica would equal Jessica's wage times time of Jessica. If I have different people with the same kind of, two different times, I usually use T with a little subscript. You can also choose a different variable, but that helps me remember exactly what it is. Okay. So I actually have, a few different versions of the favorite equation I can make there. Okay. Let's think about where else we might find one. How about the house was priced at $100 a square foot? What about the total square feet? What might be a version of the GMAT's favorite equation where we're talking about total square feet? And there's no right answer to this, by the way. I'm just curious what we might think about. Total square feet, what is that going to equal? Well, if it's a rectangular house, you could say it's base times height. You could say if it is a rectangular house, you could say it's the length times the width. Let's assume it's not a perfectly rectangular house. Could be the sum of the areas. That's a good, yeah, Danielle, good point. It might just be like, I don't know, add up all the areas. But so that would be one way to get the total square feet. What would be a GMAT's favorite equation way of getting the total square footage in a house? And hint, just because, it might not be talked about in this sentence, I'm just trying to stretch your ability to see how this equation can show up. See, a lot of people talking about price. That's just a reformulation of the equation we already have, I think. Yeah, you could divide the total price by 100. That's the equation we already have, just retooled. I want a new equation that could calculate theoretically the total number of square feet. Danielle, I think that's getting closer. I don't know exactly what we mean by area by number of areas. I'm going to reframe that just a little bit to be maybe a little more clear. It's like, let's say square foot per room on average, right? Average square foot per room times number of rooms. Now, I know this sentence didn't talk about number of rooms. Maybe another sentence would. My point, the point of today's lesson is that like the truth of the favorite equation is there regardless if it's in the problem or not. Doesn't matter what the situation is. The total square footage of a house is the average square foot per room times number of rooms. That's guaranteed to work. Doesn't matter if it's in the problem or not. Okay. Sarah's income is her wage times her hours worked. These are just there. Okay, they're just part of life, just an objective truth. Okay. For instance, how many items does this store sell every week, right? Total Q sold. Well, it equals, I don't know, Q sold per day times 7, assuming the store is open 7 days a week. Right? I can find other versions of this equation. They're just there. Just if you take some total, I don't care what the total is. It can be square footage, it can be students, it can be light bulbs, be whatever you want it to be. If you can think of a way to break it into an average and then multiply, average light bulbs per room, average light bulbs per lamp, whatever it is, right? The total light bulbs equals light bulbs per lamp times number of lamps. Guaranteed to work. And part of the difficulty, and this is what we're going to get to in this last version as well, is that a lot of times we have to set up a few of these equations and see how they relate to each other, right? To take this version of the equation and use it in this version of the equation for that Q. It's not uncommon to have to use multiple iterations of the favorite equation in a single question. So what versions of the favorite equation can we see in this little paragraph here? Okay, so night crates, let's call that crates at night equals 2 nights, the crates in the day. That's one version of this equation we can definitely use. What other could we use? What other could we find? Let's say the night crew, the number of people in the night crew, good, Daniela and Monica, I'm seeing a few people say this. The night crew is 1/10 the day crew. For every 1 person at night, there are 10 people in the day. And if I multiply that by how many day people there are, that gives me the number of night people. Good. What other versions could I make here? Nice, Daniela. Very nice. The total number of crates moved at night equals however, the rate of the night crew, the crates per person, times the number of people at night. And this is the one that's hidden there, right? There's not text to know to say this necessarily. It's just something you have to recognize. Total crates at night equals crates per night crew member times night crew members. Where do you suppose, Daniela, I say there wasn't textual support for this, there is some textual support. Where do you suppose the textual support is to think about this version of the favorite equation? And similarly, we could do one for the daytime. So Danielle, if you're saying it's that sentence, that is right. There's a single word I think we should start noticing. And there are a few other words we'll talk about that really tell you to think about this, this favorite equation. What single word in the question would tell you to maybe think about these versions of this equation? Average is a good answer. Yes, Adnan, I would say that is one word that tells you to think about this. There's one other, but that is as good an answer as the other one. It's not the one I was thinking of, but you're totally right. What other word in that sentence? Times, kind of, Danielle. That's actually going to be a different, that's going to end up being a different version of the equation we haven't even seen yet. That would be the one you make to finally solve the question. Yeah, Eugene, that's it. Each average, each night member. Words like each and per and total and in all. Those are really good indications that some version of this equation should be used. Okay. Definitely want to keep an eye out for those. Average is a good an average is a per unit measurement. anything. Very good. So we're not actually going to solve this question, partially because by solving it, I think we'll spoil the question we've already done that we want to come back to. But this should be a good hint as to one way you might do it, and certainly a good start that could get the gears turning. So we will return to that question shortly. Before we do that, we're going to do a few other questions here. This is one I've done many times in free GMAT prep hours because I think it's just such a useful question. The goal here is not to do the problem. The goal here is to list as many ways you can think of to use, or you could use, the GMAT's favorite equation in this problem about orange juice, concentrate, water, and orange juice, and servings, and all this stuff. Because this question is loaded. It's basically, whichever way you do it, it's basically running the GMAT's favorite equation several times in several different ways. So I'm going to give you here 2 minutes or so just to brainstorm, just think as many ways as you might use the favorite equation as you can think of. Now, for the sake of time, go ahead and type in the chat when you think of one. I'll just start listing on the screen. So Adnan, that is an equation. It's not a version of the GMAT's favorite equation. All right. I have some answers in, but it seems like we're kind of struggling with this one. Just a few versions of this equation that would pop up here. I mean, the easiest would probably be total ounces equals 6 times 200, right? Ounces per serving times total serving. Ounce per serving times number of servings. That tells you how many orange juice ounces we need to make. It's going to be 1,200. We're asked how many cans of concentrate. So, and we have 12-ounce cans, we could say ounces of concentrate is going to equal 12 times the cans of concentrate. You could say cans of water is going to equal 3 times the cans of concentrate. There's 1 can of concentrate is mixed with 3 cans of water. So if you want to figure out how many cans of water you needed, take how many cans of concentrate there are, multiply by 3. You could say, like, I don't know, what would it be? It would be, not cans of orange juice. Oh, yeah, I guess it would be. If it was cans of OJ, would be 4 times the cans of concentrate. Why? Well, every can of concentrate is mixed with 3 cans of water to make orange juice. How much orange juice is that? Well, every can would be 4 cans because it's 1 can concentrate, 3 cans water, 4 cans of OJ. So total OJ would be 12 times the cans of OJ, 12 ounces a can. How many cans of OJ do we have? There are a lot of different versions of this this favorite equation in this problem, and you use them to answer it. I mean, I'll just show you one solution path, and if you want to see others, you can watch videos. I've done several solution paths to this. Excuse me. But if I needed 12 ounces total, 12 ounces of OJ. Well, I would know that cans of OJ would be 12 times, would be 4 times cans of concentrate. And that's what I want. I want to figure out how many cans of concentrate I have. Okay. Well, every can of concentrate is 12 ounces. Okay, so ounces of concentrate equals 12 times cans of concentrate. I'm really going through this in an obfuscated way because I'm trying to emphasize this equation as much as I can. Okay. Well, that means there's going to be 48 ounces of OJ per can of concentrate. 12 ounces a can, 4 cans of OJ made. That's 48 ounces. So if I want to figure out how many cans of concentrate I need, I can do 1,200 divided by 48. And that looks pretty gross, but if you simplify down, you can divide by 4, for instance, and you can say that's 300 over 12. That's just by dividing both top and bottom by 4. That's going to be much easier because 300 divided by 12, well, that's 60 times 5 is 300 divided by 12. That's 5 times 5 is 25. So I need 25 cans of concentrate to make 1,200 ounces of orange juice. That was not the clearest way to work through that problem. I apologize. I wasn't planning on actually doing it, but I've done this question in several recent free GMAT prep hours. Okay, and all of them, all the paths, all the different solution paths require different versions of the GMAT's favorite equation. Be on the lookout for it. Use it again and again and again. How about here? Different word problem, take 2 minutes. This one we are going to actually try to solve. The way to solve it is going to use the favorite equation. That last question is average difficulty shot. This question here is a little bit harder than average, I suspect. That's 2 minutes. Take about 10 more seconds here. Okay, so I have one answer in, so I suspect we struggled with this one. First off, let's indicate where in the question we see hints to use versions of the GMAT's favorite equation. Well, we have total, a total cost with a certain number of something. Okay. We have another total cost. We have each toothbrush costs the same amount. How much did Misha pay? That's a price for a single toothbrush. We have all these differences between the total cost and the individual cost. So I could say that the $60 total cost equals the price per toothbrush, which I don't know, times the number of toothbrushes, which I also don't know. But that's just something I get from that first sentence. $60, how many toothbrushes, and how many dollars a toothbrush. Okay. Then I get a new situation. I'm told that if she buys 5 more toothbrushes, and I'm in a new situation where I have actually the same total cost, but the question becomes, well, what is the new price? And what is the new toothbrushes? I'm using these P and T are different than this P and T. These actually stands for the values, the price, and the number of toothbrushes. This stands for what is the price in general and what is the number of toothbrushes in general. Well, I'm told the price is a $1 discount, so I can write that as $1 less than the original price. And the number of toothbrushes is 5 more than the original number of toothbrushes purchased. So I can say that that's number of toothbrushes originally purchased plus 5. And I can set up these two equations. These are the two versions of the GMAT's favorite equation that show up in this problem. 60 equals price times quantity, and 60 equals price minus 1, a new price, times t plus 5, a new quantity. Now, solving from here, if you try to do algebra, you're probably a little bit bummed out, because the algebra here is not easy. It's pretty gross. It's not my favorite thing to do. This is not a lesson in back solving, but this is the perfect problem to back solve on. Okay, plug in 5 for the price. It's going to be 12 toothbrushes. Plug in 4 for the price. That's going to be 15 toothbrushes. Plug in 3 for the price. That's going to be 12 toothbrushes. $1 is not going to work because a $1 discount off $1 is silly. So let's say 6 for the price. That's going to be 10 toothbrushes. Well, we can then test the new situation. If it's 5 and 12, it's going to be 4 and 17. $1 off, 5 more toothbrushes. Is that 60? 4 times 17 is not 60. 4 and 15, $1 off is 3. 5 more toothbrushes is 20. Hey, there we go. That's ugly looking, so I'm going to make that a little neater. Here is the situation that fits the problem as written. Okay, so the answer is going to be C4. And back solving is clearly the way to do this question. Algebra is a nightmare. A good question. How did I think to back solve instead of doing algebra? Well, for one, this thing looks like a quadratic. If you don't know that, you will as you study. Quadratics and back solving are pretty good friends on the GMAT. A lot of times the algebra is not the easiest way. So on especially word problems, if it looks like a quadratic and it's a word problem, I often default to plugging in answers and seeing which one works. The other way to know that this back solving is a good option is that look how easy the answers are, right? It's not like these answers are really hellish. These work really nicely with $60. And so if I can just plug them in, I can figure out how many toothbrushes, everything just works out from there. In general, students are way too fast to default to algebra. Algebra is one tool of many and not always the best. Make sure you have other tools on your toolkit. Okay. Having said that, here's another question. Take 2 minutes. Let's see how the GMAT's favorite equation might show up here. 2 minutes to 10. In order to solve this question, or one way to solve this question, is to set up 2 different versions of the GMAT's favorite equation using total vehicles, vehicles per day, and number of days. I don't have any answers yet, so I suppose this one is challenging, and it's probably the hardest one we've seen yet, so it's understandable. There's a B coming in. Okay. The equation we can build on that first sentence. What does that equation look like? Yeah. Total, the number of vehicles, let's use V, because why not? Vehicles equals the number of vehicles a day. Well, I'm told that that's 40. And then I'm told, well, I'm not told, there's a number of days to fulfill the order. So whatever that number of vehicles is, it's 40 times the number of days to fulfill the order. Turns out things didn't go so nicely here. But I'm still in a situation where I can use my favorite equation. For one, how do I know? 32 automobiles a day. There's my vehicles a day. The question is, how many vehicles do I make? And for how many days? And it becomes a iterated game. You have how many vehicles, rate per day, number of days. How many vehicles, rate per day, number of days. What is the number of vehicles I make? This machine makes when it's working at 32 vehicles a day. It doesn't make V, right? Because V was the total number of vehicles. Whatever V is, that's all the vehicles. How many vehicles does it make? Maybe let's start with days. Shall I see you wrote something that's very applicable here, right? How many days is this thing working at 32 vehicles a day? It's not D, because D doesn't stand for days in general. It stands for the specific number of days I have for this order. So how many days does it work at 32 vehicles a day? Every day except the last 3. So however many total days it is, I subtract 3. Yeah, there you go, Jordana. And the number of vehicles is the total number of vehicles minus that 264. That I haven't made yet, right? For the first amount of days until the last 3, I was at a rate of 32 vehicles a day, and I made this many vehicles. I don't know the exact number, but I know it's 264 less than the total because I have 264 in the last 3. Okay. And from here, it becomes a game of salt. You substitute in for 40D because that equals V. So you can say 40D minus 264 equals 32D. 32 minus 32 times negative 3 is 3264 minus 96. I'm going to subtract my 32D from 40D, and I'm going to get 8D. I'm going to add 264 to negative 96. That's going to be 264 minus 96. And I do that is, okay, 64, and then minus 96 is another 32. So that's going to be 200 minus 32 is 170, 168. Divide by 8, and I can see that 8 goes into 160 20 times, and there's going to be an 8 left over for 21. Okay. So it's one way to solve this equation. It's just how many vehicles at how many vehicles a day times how many days. And you think of different ways to represent that, to set up the 2 equations, and then you just substitute in, hey, this value, that is V. So I can just plug that in for V. Okay. Another kind of nifty way to do this problem. I was supposed to make 40 a day. I didn't. I made 32 a day. for some number of days, d minus 3. So that means I'm falling behind 8 every day times some number of days, whatever the total is, minus 3. Then I do 264 in 3 days. When I'm catching up, I do 264 in the last 3 days. So that's going to end up being, well, 264 divided by 3, it looks like it's going to be 88. Well, 88 is plus 48 every day. So I make up 48 times 3, which is going to be, let's see, 50 minus 2, 150 minus 144. Well, that amount that we caught up, the extra ones we made in the last 3 days, those are the ones we fell behind for the first amount of days. So that has to be the same. So I can say 144 equals 8 times however many the total days is minus 3. So if I divide 144 by 8, that's going to equal d minus 3. I know this is going to be 18. Plus 3 is going to be d, so that's going to be 21. That's a very sneaky, tricky way, but I just think it's a nifty little approach. Still uses the GMAT's favorite equation. It's just instead of total vehicles made, it's total vehicles behind equals vehicles falling behind a day times that number of days. Number of days falling behind, right? We use that equation to figure out how far behind we are on this order. And we're falling behind 8 every day because we were supposed to do 40 and we actually do 32. How many days? Well, whatever the total is, less 3. Okay, well, how many do we need to catch up? Well, that's going to be whatever extra we make in the last 3 days. We're supposed to do 40, we make 88, that's 48 extra. For 3 days, that's 144 extra cars in the last 3 days. So that's the one we make up. So it has to match. Very sneaky. I just think it's nifty. Different use, still the GMAT's favorite equation. Okay. I'm going to put this up here, and I'm going to suggest that those of you that are watching from home hit pause and do this question. I'm afraid for the live audience, we're going to go past this one. The point of doing this question at all, there are a few ways to do it, but to use the GMAT's favorite equation of it, the way I was going to use it was just to demonstrate that percents are really not different than this favorite equation we've been talking about, because every percent is a ratio. And if you watch All About Percents Part 1, another free GMAT prep hour, I really go into that and lay out how a percent is just a ratio. The ratio of A's per B, if I tell it as a percent, it's how many A's there are for 100 units of B. It's the same idea. It's just that instead of a, I'll show you guys, it should not be an equal sign. It should be a multiplication sign. Instead of a ratio pared down to its most simple form, we've set the denominator to 100, basically. Okay, so if I say that food X and Y, food X contains 10% protein, well, then I can say protein from food X is going to equal what? What would the total protein from food X be? One-tenth of what, Monica? Not 1/10 of 300, because 300 is the total grams of the mixture. And I know we're doing this a little fast, so you might not see that, but it's going to be 1/10 the total food X, right? Because it's 10 grams of protein per 100 grams of food X, right? 10 grams protein per 100 grams food X. And that simplifies to 1 gram protein per 10 gram food X. Same information. Not different at all. Okay. So I can get that amount of protein from food X. I can do the same thing for food Y. It's going to equal 0.15. 15 over 100 times total food Y. Okay. I'm going to leave it to you all to come back to this problem and finish it. That's a pretty solid start. You can then think about, well, what's the total mixture's food going to be? It's not quite the GMAT's favorite equation. It's just adding the food X and food Y together. But you set up those equations, you're on the right path to solve. So percents and this game, really not all that different. Oh man, there's so many other questions I wanted to do. If you have to leave, of course, feel free to. I'm going to keep talking. So those of you that want to stay, we're going to get a little bit extra, a little bit longer than an hour today. Let's jump to a verbal question, because I did want to show how this shows up in non-math problems, or at least ones that don't look like math right off the bat. This is a critical reasoning question. So go ahead and take 2 minutes. That's how long you have for these. Choose your best answer here, and I'm going to talk about how the GMAT's favorite equation is totally applicable to this problem. No worries, Eugene. See you later. 6 more seconds, everybody. All right. So why is the mayor of Frelonia so worried? Well, because there's a version of the GMAT's favorite equation in play here. The total passengers on a train equals passengers per car times number of cars. And the new rule is going to make the number of cars to go from 25 to 20. We're losing 5 cars. Oh no, quoth the mayor. This is a disaster. All the people who come to our city to buy stuff, we're having, the trains have fewer cars now. The mayor is saying, well, because we're losing a number of cars, we're going to lose tourists. Notice though, when you're thinking in terms of the GMAT's favorite equation, there's a huge question mark right there in the middle. What about the passengers per car? If you watch the free GMAT Prep Hour critical reasoning games, it's one of the first one I ever did. Might be the first one I ever did. We talk a little bit about this kind of critical reasoning question. It's not uncommon. And it's just the GMAT's favorite equation. We don't have to do math calculations purely, like we don't have to use the numbers, but you have to have a quantitative understanding of this relationship because a lot of critical reasoning questions use it. If the number of passengers per car can increase enough such that the decrease in the number of cars is mitigated, is taken care of, yeah, we have fewer trains per car, but we don't necessarily have fewer passengers. I'm sorry, we have fewer cars per train. But we don't necessarily have fewer passengers per train. Okay. And so the answer that deals with this part of the favorite equation is D. If the train cars, I chose 75% because it's a little bit tricky, but imagine it said 10%. Or imagine if it used the word only. That tends to do wonders for clarity. The fact is that there's room in those cars to make up for the loss. Now, if they were 90% full, 99% full, maybe not. So you do have to do a little bit of quantitative reasoning here to understand that the 20 to 25, the 25 to 20 change is a 20% change in the number of cars. But if we fill up the cars that remain from 75% to 100%, it's more than enough to make up the difference. So even though, yeah, we're losing cars on the train, we have plenty of seats left on the trains to fill up, so it's not a problem. Is there an argument to be made that if the maximum capacity is decreased, the average utilization will also decrease? Shaw, we would not be able to assume that without information. We would not be, yeah, we would need to know that that is the case. We can't assume that that is the case. What I call that thinking Shaw. What Shaw is basically saying is like, well, hold up. What if, you know, people don't want to ride on crowded trains, and so if each car is more filled up, people actually just don't come anymore, right? So we actually do lose the number of passengers per train. That's very possible, but what I call that is blowing the feather back. And that's, you shouldn't do that in a critical reasoning question. What D does with the information we know is weaken the argument. Is it possible that something else could be true such that this thing that weakens the argument actually doesn't weaken the argument? Sure. Of course, there could be a new piece of information that could undo this weakener. Okay. That doesn't matter. Based on what we have, on what we know, this still weakens the argument. The fact that there's a possibility it doesn't matter. It blows the feather in the direction of a weaker argument. So it's not your job to blow the feather back. You just recognize, oh, the feather's blown in weaker, it's weaker. You don't have to say like, yeah, it's weaker, but if I blow it back, it doesn't have to be weaker. True, but as written, it's weaker. Okay. So all these other ones are tempting. Some of them are tempting, but they're not right. Okay. If we lose the low spenders, doesn't matter. That's still less money. Doesn't matter if we lose low or high spenders. Fewer spenders is money lost. Number of trains, sure, but the point is we're losing number of cars on each train. So B doesn't do anything to weaken this argument or strengthen. Some people travel to other places. In fact, most people travel to other places. Well, that's true already, right? I never say that we need to get everyone on the train or majority of the people on the train. The point is some people from the train step off at Furlania. So C is out. In fact, it tells us, where does it say? Popular destination, most visitors access by train. So most visitors to Furlania access it by train. It doesn't matter if a lot of people on the train don't stop in Furlania. E is talking about other trains that have smaller cars. It's not relevant. We're talking about most of the trains, because it says most trains are going to have to lose cars. Okay, so D is the one that is correct, and it deals directly with the GMAT's favorite equation. I'm telling you, this thing shows up everywhere. So we're going to come back to the first question. I want you to try it again with this free GMAT, or sorry, with this GMAT's favorite equation in mind. Let's see if we can get to an answer and more cohesion this time. I'll then stick to do a bonus question, but I want to make sure we come back to this one for the people who stuck around. That's two minutes, everybody. So first I'm going to go through kind of a pure algebra way to do this. Then I'm going to show you, I think, what is probably the better way to do this, but just to demonstrate the value of this, understanding this equation. Okay. We have a price of fixing things, and we have two different kinds of things. We can think of total revenue from desktop that equals the price of the desktop. Here, I'm going to do use this, even though it's going to be a little sloppier, but it's better in the long run, I think. So revenue from desktop service is going to equal the price of the desktop service times the number of desktop computers serviced. And similarly, the revenue from the laptop is going to equal the price of a laptop times the number of laptops serviced. And of course, overall revenue is the sum, the revenue from the desktop plus the revenue from the laptop. That's going to give you total revenue. Well, then I'm told that the price of fixing a desktop is 2/3 the price of fixing a laptop, and I'm told that the number of desktops served is 3/5 the number of laptops served. So I can substitute those into the revenue from the desktop. The revenue from the desktop is the price of the desktop, which is 2/3 the price of a laptop, times the number of the desktop, which is 3/5 the number of the laptop. So that's going to be 2/3 times 3/5, and I'm going to say that's 2/5 the price of a laptop times the number of laptops. That's probably why on the first pass we had quite a few people choose B, because we've got 2/5, and it seems so nice. That seems a little too easy though. That's just 2/3 times 3/5. You have to remember we're asked about the fraction that is desktop out of all of the revenue. Well, what's all of the revenue? It's the revenue from the desktop plus the revenue from the laptop. Well, what's the revenue from the laptop? Price of laptop plus number of laptop. What's the revenue from the desktop? 2/5 the price of the laptop times the number of the laptop. and I put that revenue, 2/5, the revenue of the desktop, over total revenue. And here's the nice thing, all of these multiply. Looks like a plus there. I feel like I miswrote something. It's the price of laptop times number of laptops. All of these are in terms of PL number L. And so that actually just cancels out. So this becomes just 2/5 over 1 plus 2/5. If we just call this, RL, then we have 2/5 RL over RL plus 2/5 RL, which becomes 2/5 over 1 plus 2/5, which is 2/5 over 7/5, which is 2/7. And that's A. Now that's not my favorite way of doing this question at all. So we're going to go through a better way here in a second. But I just want to show you how you can, if you do the algebra, if you use the equation and are clear on what each version of the equation is, set it up carefully, you can work through this algebraically. First off, I do want to point out that there are fewer desktops served and the desktop is cheaper. So that means it has to be A or B. If you had to guess, you're already at a 50-50. And yes, there are questions that do this all the time. If there are fewer desktops served and each desktop is cheaper, then they are less than half the revenue. But the real key to this question is that we don't know any of the actual values. Everything here is a relationship, so we can pick our own numbers. And that's going to make this much easier. We're still going to use the favorite equation, but we're going to pick our own values for laptops and desktop stuff. So the revenue from laptops, revenue from desktops. We're told that the price of the desktop is 2/3 the price of the laptop. Well, let's just do 2 and 3. We can pick whatever we want as long as it fits that relationship. We're told that the number of laptops is 3/5 the number of, the number of desktops is 3/5 the number of laptops. Let's just say 3 and 5. Well, if I have 5 laptops and each one costs $3 to fix, that's $15 from laptops. If I have 3 desktops and each desktop costs $2 to fix, that's $6 from desktops. How many dollars total? 21. How many from desktops? 6 out of that 21. And 6 out of 21 equals 2/7. Smart numbers is easily the better way to do this question. You still need to use the favorite equation. Price times number equals revenue. You do 2 versions of it, and then you add the revenue together to get total revenue. Okay, but it's just easier to work with numbers instead of these crummy variables. So many variables to deal with here. This is, in fact, if your scratch work ever looks like this, you should look for a better way to do that question. So what I'm going to do now, since I am going long, but I do want to do a bonus problem just for fun, I'm going to hit pause on the recording. And those of you that have any questions you want to ask, but you have to leave, please feel free to ask. And then for those that want to stick around, we'll do a bonus question. Those of you that are watching on YouTube, it's not even going to seem like anything's changing. We're just going to jump right to the next question. All right, friends, we're back. Those of you that have been watching, it didn't even feel like we stopped, did it? Real quick note before we continue, just pointing out those important words that tell you to look for the favorite equation or to look for something like it. We have each, total desktops, total laptops. Those words, price, right? These words tell you to think about price, quantity, total revenue. And you can think about that for laptops and desktops. Let's do some other questions here that deal with the favorite equation. Let's look at another one. I've done this again in several recent questions, in several recent free prep hours, but I think you're surprised to see that it actually fits the favorite equation framework. So take 2 minutes here. 2 minutes. So how does the GMAT's favorite equation fit into this question? Well, we have here a number of numbers. It's a very abstract way of saying this, but it's just like, hey, we're adding up a number of numbers in numbers. Each of these numbers is either 7 or 77. And the total sum is 350. Well, so if we think about that, 350 is going to equal the sum of some number of sevens plus some number of 77s. And what does the sum of the number of sevens equal? Well, it equals 7 times the number of sevens. Let's say the sum of sevens. That equals 7 times the number of sevens. What is the sum of 77s? That equals 77 times the number of 77s. Here's my favorite part here. 77 equals 11, or equals 7 times 11. What does that mean? 77 equals 7 per 7. There's 7 units per number 7. And if there's 11 number 7s, we get 77. So I can do 350 equals 7 times 57s. That's totally fine. I can do that. Then I can do, 0 equals 77 times 0 sevens. I'm sorry, 0 77s. That would be 350. It's not one of the answer choices, though. This is also not very clear. I apologize. I didn't realize the answer choices were glitching out a little bit here. That's weird. Let's fix this. There we go. But I can't do 50 and 0. It's not a choice. But if I take 11 77s away, I'm sorry, 11 sevens away. So 50 minus 11 is 39. I can get 1 77. This mouse pad is not great. I don't know what 7 times 39 is, and I don't know I know what 77 times 1 is. I've never actually calculated 7 times 39, but I know it's that whatever it is plus 77 is going to be 350. So it's going to be 77 less than 350, so that's going to be 273. Okay, there, I did it. Kind of cheated though. I just know it's going to add up to 350. But there are 39 sevens and 1 77, so 40 is possible. Not a traditional use of the GMAT's favorite equation here, but kind of secretly applicable, right? The sum of the number of sevens, the sum of all the sevens I have is 7 times the number of sevens I have, because every 7 is worth 7 units. Seems weird to use a number to say how many numbers I have, but I have to. How did I know it's 39? Because of this exchange rate between 77 and 7. Every 77 is worth 11 sevens. And so if I add a 77 to the mix, I take 11 sevens away. I could also do 2 77s and 28 sevens. Or I could do 3 77s and 17 sevens. Or 4 77s and 6 sevens. But that's it, no more. I can't have negative amounts of sevens in this case. So it's one of these. There's only 5 possibilities here. 0 77s, 1, 2, 3, or 4. And the only one that is an answer choice is, that fits an answer choice is C. So a tricky question that doesn't immediately, it's not immediately clear how the GMAT's favorite equation applies, but it does. The sum of values equals the per unit value times how many units there are. That's the GMAT's favorite equation. It shows up again and again in a myriad of different ways in a myriad of different questions. Whenever you're looking at per unit totals and general sums, look to use the favorite equation. All right, friends. Thank you all for coming. Check out our upcoming courses. Remember, you can take the first one for free. Try our interactive 10-day Foundations of Math course. Right, and we do these free GMAT prep hours every few weeks. So I hope to see some of you back. I promise they don't always go an hour of 30 or something. This was an especially long one. But because I think this is a huge topic that shows up in many different ways, I wanted to give it its due. I still feel like we could keep going, but I can't. I gotta go to sleep. So I'll stick around now for any questions. Otherwise, see you all soon. Best of luck in your studies.